So there's a question about this exercise from the practice quiz 1, and you're told in the first part to calculate the electric field from an electric dipole. So here's our picture of the electric dipole over here. You go through, you calculate the electric field, and I think people didn't really have a question on that. So here's the electric field from electric dipole. And in the second part, you're asked to show that this goes as we expect, 1 over the distance cubed for when you're really far away from it. And so the way we did it in this exercise is we added together, so here it's a little bit of algebra, so we added together basically these two terms, and you're left with this piece here. So KQ 4AX, and you got x plus a squared times x minus a squared, and then when you make this approximation, when x is much, much bigger than a, that's approximately equal. So basically you get rid of the a's in the downstairs, and you're left with KQ 4AX, and on the bottom you end up having x to the fourth. And so this is exactly equal. You can cancel out one term of x. You get KQ 4A over x cubed as expected. Now, I say here that you can also use the Taylor series to do this, and it's a little bit more elegant. And basically, one can be easier than the other. I will say here that Taylor series is something you learn in calculus. And I kind of wish that, when I learned it, they had told me you'll probably be using this for like almost every week for the rest of your life. So it's really important in STEM, engineering, and physics, this idea of a Taylor series expansion. And so what we're going to do here is this version here, which you can also, sometimes is referred to with many names, but this is basically just the Taylor series for some sort of a term like this. So if you have something 1 plus some d to the n power, all right, that's approximately equal to 1 plus n times d plus dot dot dot. So with this series, basically we can expand this thing out to an infinite series of terms. But what happens is in a situation where this term d is really small, we only need, like, say, the first couple of terms. So this will be an example where we only need basically the first 2 terms when we do this. So you could end up being the third or the fourth, and that's where it gets kind of tricky, or at least more of a pain. But so in this case here, what I'm going to do is I'm going to rewrite this in a way that makes this a little bit clearer. So here I'm going to pull out the x term from each of these pieces. So I get 1 over x squared, and then I'm left with 1 minus a over x squared. And this one over here will be the same thing, x squared, except now this is 1 plus a over x squared. And so I'm going to use this piece here. So my d in this case will be negative a over x. And so I just plug it into my formula. So what I can do is I can make these substitutions. So this one here, so it's 1 over x squared. And actually what I'm going to do is I'm going to do one more step just to make it a little bit more clear. So 1 over 1 minus a over x squared, and then minus 1 over 1 plus a over x squared. So I just pulled out the term of 1 over x squared out of both of them, since that term is in both of them. And so then here you've got these two guys, which I can then write, like this one here, I can write this as 1 minus a over x to the negative 2 power. So I can replace this, okay, in the approximation where x is much, much bigger than a with this formula. So I can put 1, and then I'll have plus negative 2 for my exponent, and then the d is that, again, negative a over x. So for this one here, I can replace this with 1 plus 2a over x. Now I'll let you guys do this one, but the other one is 1 plus a over x to the negative 2 power. And when I do that, you'll get 1 minus 2a over x. And so now if I substitute this in, so again, this is taking the approximation that x is much, much bigger than a, right? Then I can write this over here as kx 1 over x squared, and then inside here I can just replace this with this piece, so I get 1 plus 2a over x, and then this piece over here will be negative 1 minus 2a over x. And we can just go through and do this. So here you'll see that the 1's cancel and this negative sign turns this to a positive, and the 2a over x add up. So I have 1 over x squared and then 4a over x times this other piece. And you'll find that when you clear this up a little bit, you get kq 4a over x third, which if you go back is the same thing we got over here. So it's just another way to do it. Basically I think this is a little bit more elegant, and this way can be faster because what'll happen is sometimes trying to do this business over here where we just sort of added these two fractions together can get really messy. And so this will be in general a little bit of a nicer way to do that. I'll also post a video about just explaining more about the Taylor series, because it may be something that you haven't used too much. Hope this helps.